Substance. Stories about the stuff that shapes our world.
Instead of trying to kind of start from scratch, or instead of trying to kind of ignore knowledge that exists. I mean, knowledge is a resource the same way energy is a resource. Instead of, trying to just force oneself to creating something original, there's a lot of inspiration that can be a great starting point for creating something novel.
Substance. It's July 2026, summer here in the Northern Hemisphere. I'm recording right now in Texas, and it is hot. And if it weren't for the air conditioning, I'm not even sure I could stand to be in the studio right now. Of course, my comfort comes at a cost. My air conditioner sucks up a huge amount of electricity. A recent International Energy Agency analysis found that over the next decade, cooling will be the leading driver of energy demand in built spaces. We're talking homes, offices, factories, and data centers. Still, as the world warms, cooling isn't just a luxury, it's a necessity. Some places will become dangerously hot, both here in the United States and across the world. So we need innovative ways of cooling the spaces that we inhabit that don't increase the amount of energy that we consume. And maybe the answer doesn't lie only in making air conditioners more efficient, but also in understanding how people in the past stayed cool, especially in places around the world where heat has always been a concern. I'm Joe Hanson, and this is Substance, a podcast about the discoveries and innovations in chemistry and beyond, helping us build a sustainable society for the future. In short, we tell stories about stuff that shapes our world. Humans have shaped the world with this substance for all of human history and much of prehistory too. I'm talking about clay. Now, the oldest known clay pottery is 16,000 years old. The oldest clay brick homes date back to the beginnings of agriculture. Of course, like everything else, clay has its own chemical makeup. It's just a composite of tiny mineral particles made mostly of aluminum, oxygen, and silicon, a few molecules of water tucked inside, and sometimes with some other elements thrown in. That means we can still use the power of chemistry and other modern techniques to push the bounds of what clay can do. So in this episode, we're talking about how to make what's old new again, how the past can inspire the future, and how we can still innovate with one of the oldest substances used by humans. Brook Kennedy will join us to explain how 3D printing allows designers to play with shape and aesthetics to make ancient technologies contemporary. And later, Reuter from BASF will tell us how the innovative Cavipor, a breathable clay-based insulation material, is already protecting thousands of older homes across Europe against both heat and cold, with no need for invasive retrofitting.
Speaking overall, I think there are a lot of technologies out there that we got rid of without really giving them a second chance. And especially as society has changed and the focus and priorities have changed. For example, no one really cared or was worried about the environment or the climate, 150 years ago. So a lot of technologies that were maybe more able in that regard disappeared.
Substance.
My name is Brook Kennedy, and I'm a professor of industrial design at Virginia Tech in the United States.
You maybe have never heard of industrial design, but think of the air conditioner that's keeping me blissfully cool right now, or the microphone that I'm talking into, or the chair that I'm sitting on. An industrial designer probably had a hand in creating each of these, and just about everything else that's around me or you. Brook says that industrial designers have an important role to play in creating a more sustainable future, in part by taking cues from the past. His 2023 book, Reimagining Alternative Technology for Design in the 21st Century, explores alternative and traditional technologies that have, for various reasons, been abandoned in pursuit of the new, shiny, and so-called modern.
I use this term innovationism that, I think sometimes new technologies are adopted not because they're better, but because they're interesting and that people are fascinated by them, that people are somehow smitten by their novelty. I think there are a lot of technologies now that we've so eagerly adopt without really understanding their consequences.
Inspired by some of the traditional cooling technologies described in his book, Brook and his collaborators are exploring a next-generation method of cooling. The multidisciplinary team developed a new kind of sculptural room partition that can cool a space without consuming electricity. And you guessed it, those partitions are made from clay.
I think ultimately I came into design out of an interest in making things and using my hands.
As a student, Brook thought he wanted to be an architect. But after a couple of internships, he realized he didn't feel as passionate about designing on the large scale of a skyscraper or even a house. He wanted to visualize objects and bring them into reality where they could have an impact on the physical world and the people who use them. It turns out that what he loved doing was exactly the work of an industrial designer, even if, like most people, he'd never heard of the job.
And I looked around and at various built things in my environment that I loved or hated or wanted to change and just asked, who builds these things? What is the profession that is engaged in it? I kind of stumbled across this happily. And once I found it, I couldn't go back. I designed about 70 products that went to market. I have a lot of patents and, a lot of the work that I did was a lot of recognition, sort of with awards, et cetera. But I think something that kind of left me feeling maybe a little bit incomplete is designing a lot of stuff that didn't really last very long and ultimately it was wasted. I became more interested in circularity, more interested in the environment, more interested in health, and especially trying to see how industrial design, which is inherently, I think, commercial, how it can support the creation of goods and services that are more meaningful, that are longer lasting, that can be repaired and ultimately are more circular. I started as a professor kind of as a second career. I came back and went to the university setting because I'm interested more in kind of big picture problems or sort of larger global concerns and how human-centered design in part, can fulfill and serve these goals.
Human-centered design focuses on the person who will actually buy and use an object.
Understanding in general what guides people to choose one type of product or another is ultimately kind of a black art. It's really understanding what makes people tick, what makes people at very least buy, but also what are the kind of underlying needs, fears, hopes, desires that people have that ultimately make them gravitate to sort of certain types of products or experiences rather than others.
Brook says that human-centered design can also generate objects that, in the long term, aren't good for us or the environment.
Sometimes human-centered design can be because it's very commercial, it's very much about sort of favoring what's convenient and what's easy over what is ultimately good for the environment, or even what's good for the individual's health in the long term.
A soda served up in a plastic bottle is convenient, tastes delicious, it's refreshing, cooling, but the bottle might end up in a landfill, or worse, floating in the ocean. And the soda isn't exactly the healthiest beverage choice. Brook says that tension is one of the reasons he left the business world and sought out a career in academia in order to employ human-centered design in service of sustainability.
When I came to academia and I was interested in circularity and I was interested research into design that I think was more about questioning and trying to solve grand challenges in society, whether that's access to water or improving the environmental performance of various products. One area that I was always very interested in, I guess you would call it legacy or ancestral technology. So that was sort of the beginning of my interest in cooling technologies, because I always sort of asked the question, I mean, how did people maintain some level of thermal comfort before air conditioning existed?
We've encountered the idea of circularity again and again on this podcast. At its core, circularity involves taking something old and making it new again, finding another use for it. Though we normally think of this in terms of objects, Brook says that knowledge itself can be recovered and remade. He says that examples abound of cooling technologies that we've known about for centuries, but researchers haven't spent a lot of time studying them.
In a way, there are a few examples of passive cooling that have to do with evaporative cooling that are very highly publicized and studied, or at least cited, but researchers and scholars haven't spent enough time going really deep into these systems.
Passive cooling involves cooling a space without using any energy from electricity. For example, the way the shade of a tree passively cools a park bench, or a breeze flowing through an open window might cool your room at night. Evaporative cooling is a form of passive cooling that takes advantage of the fact that when water evaporates, it cools the air around it. That is why sweat cools you down on a hot day. It turns out that many of the so-called legacy and ancestral technologies that inspired Brook can cool spaces quite dramatically.
I think everybody who reads about these, who has any interest similar to my own, just goes nuts, thinking that this is all done without any energy use at all.
Some of the most impressive examples of passive cooling are found atop traditional architecture throughout the Middle East and Northern Africa. Wind towers, some dating back thousands of years. These hollow pillars with openings at the top catch cool air from prevailing winds to flow through the building that they're attached to. And when combined with the evaporative cooling power of water from aqueducts or fountains, some wind towers from Iran can cool a space as much as 12 degrees Celsius. That's more than 20 degrees Fahrenheit. Other centuries-old objects also use evaporative cooling on a much smaller scale. The Spanish water jar, botijo, cools the water inside by taking advantage of the fact that water evaporates through the pores in clay. The double-walled Zier pot, also called a pot-in-pot refrigerator, dates back at least 5,000 years and uses evaporation of water poured between the two walls to refrigerate fruits and vegetables stored inside. Another kind of clay jug, named for the capital city of Oman, called a muscates, is placed in windows to enhance the cooling power of a fresh breeze.
It's a unit that is placed in conjunction kind of with an awning and a trellis, so it blocks the sun load from coming in. But the main feature is a clay pot that's filled with water, and the water essentially passes through the wall of the pot and it evaporates. And when it evaporates, it takes heat energy with it, or the heat is dissolved by changing the water from water to its gaseous form. And then when wind passes over it, it cools. So in a way, it's kind of like a pre-air conditioning, like window unit. So people have studied it and referenced it. But again, I mean, not enough attention has been placed on really understanding how to optimize these features. And that's where my project tried to, with my collaborators, we tried to take it a step further by kind of advancing some of the means by which clay can perform better in terms of the evaporation process.
Brook worked together with the architect Stefan L. and the building systems engineer Georg Reichard, as well as with a number of engineering and design students.
I think in each of our roles, we brought some fundamental skill together.
Brook brought his experience designing objects and his knowledge of traditional cooling technology. Stefan brought his understanding of space and his experience with 3D design tools. And Georg brought a passion for evaporative cooling and the technical know-how of how to test the cooling power of the team's creations.
There have been a lot of people who've sort of toyed with these ideas, And I think part of what we did, we were one of others who were interested, but part of what we did is that we had access to a clay 3D printer, a large-scale 3D printer. And it occurred to us that if you would increase the surface area of the clay pot, like the clay pot that you see in a muscatel is smooth. Spanish botija, it's the same, it's smooth. But with a 3D printer, a clay 3D printer, you could modulate the surface with more of a bumpy surface, if you will. And by creating these bumps and these little sine curved surface texture, that increases the surface area of the surface, so you can effectively evaporate the water faster just by increasing the surface area.
Much of the experimentation in figuring out how to work together with the 3D printer and actually achieve objects with that increased surface area, well, that fell to the students. They looked at how thin the material should be, how closely together the columns should be placed, and just how to work with 3D printed clay.
Someone has to stay there and actually wait for these things to get printed. And often they fail. And often, there's a shape you might like, but you start to print it and then it collapses. There's also a lot of preparation work of rolling out. We used a lot of porcelain. And you sort of roll it out. It's almost like dough, like making bread. You have to sort of knead it and get all the air out of it, in this case, and then prepare it to be printed. So this can take an awful long time. And we believed that, by experimenting with that, not only would it increase the speed of evaporation and potentially the cooling efficacy, but it also was an aesthetic thing as well. That we felt that very often, cooling systems and sort of HVAC systems, they're often buried in the wall or out of way, so you can't see them because they're very mechanical and sort of not appealing or attractive. But we realized with these 3D printed clay columns that make the partitions, that we could really play with this sort of the surface aesthetic design of the texture, like the 3D texture of it, and such that it could be left out in the open as something that's more celebrated. It's something more of a central design piece of a home or of an office or an outdoor space. So that was sort of, in a way, I think when the light went off and we realized there was sort of a functional and an aesthetic benefit to what we were doing to take this area of research further.
Brook says that the aesthetic benefit isn't just to catch people's attention. It's actually a key feature of these cooling partitions. Because when the ugly mechanical workings of a cooling system hide behind a wall, it makes it invisible. It alienates us from the source of our comfort and the energy it consumes.
There's so much room for further exploration and optimization. But we do think that one thing that's very important about it is in a way taking a technology such as cooling out of sort of the basement or the wall or within a black box and bringing it out into the open to make you more aware of it and aware of really what it means. Because so much, especially when you think about mechanical air conditioning, it's out of sight, out of mind, but quietly it's using a ton of energy. I mean, in the United States, it's, roughly 20% of all electricity used in homes. Electricity or air conditioning adoption is increasing crazily around the globe. So anything you could do that's passive, I think, is critical. And I think with this, we're not saying throw away your air conditioner. There's no, this can replace an air conditioner. We're thinking about it more additively. All these technologies could be used in tandem to help save energy in the name of human comfort.
While the project is still in its experimental phases, Brook says that these kinds of partitions could turn up in all kinds of spaces.
I could see these in public urban spaces. I could see this in private homes. I could see this in public buildings, especially buildings that have already things like fountains in internal courtyards. There are lots of precedents in Roman and Renaissance architecture that, in a way, are working in this space already, but sort of modernizing these techniques while honoring their past towards, I think, a more sustainable future.
In the future, Brook says the team wants to figure out how to integrate rainwater systems so that these kinds of partitions don't solely rely on municipal or well water. Since clay can be sculpted into almost any shape, Using rainwater could also allow the creation of cooling sculptures that might serve more than one purpose.
And so if you imagine like a bench, or especially if there's sort of interesting 3D printed shapes that you could sit on, when you sit on them, they're cold. And so that could be another sort of dimension. Instead of benefiting from the cool air that passes over them, you to actually just sit on these things. So they could be under, like in bus shelters. Imagine a bus shelter that collected rainwater, and that water would come down and fill an evaporative cooling bench as you waited. Something like that, or in a subway or a park.
Another way Brook and his collaborators are trying to move the technology forward is by exploring ways to make clays and similar materials that can themselves be made more sustainably. Today, clay needs to be heated up to really high temperatures in order to make it both hard and stable.
One area in particular that we are trying to figure out where to pursue funding from, I think is particularly interesting. It's about trying to create a material that does not need to be fired. You have to heat up clay in 1,600 degrees Fahrenheit or more. The numbers I can't really remember, but it's quite high.
For most purposes, clays actually require firing at 11, 12, 13, even 1,400 degrees Celsius. That's 2,000 to over 2,500 degrees Fahrenheit.
I think if you're trying to tell a story which is ultimately about saving energy, I think the firing of clay remains one of the components of that story that isn't consistent with the other goals of the project.
Brook also thinks the partitions could make the most difference in combination with other passive cooling techniques that have been abandoned with the advent of air conditioning.
A lot of the audience for my book really is the United States, who has really more completely abandoned things like shutters or building houses with thicker walls. I think when it comes to things like cooling, I think there's a certain type of knowledge that's out there that, like I said, has been forgotten. And in a way, that knowledge needs to be maintained. It needs to be taught in school. I mean, both my wife and I remember how when we were kids, they taught us how to brush our teeth in school.
Brook says that just like we teach kids the right steps to take in toothbrushing, we should be teaching the steps they can take to ensure that the spaces that they inhabit are cool and comfortable. Imagine an elementary school project that tests the difference in temperature in a room with and without closed shutters, or a high school physics course that calculates how fast heat travels through walls of different thicknesses or made with different materials. He says everyone could also stand to rewire their own habits to think about what they're trying to achieve when they absent-mindedly flip on a switch.
At my office today, I'm really amazed that people will come into my office regardless of how warm it is outside. Sometimes it's still 65 degrees Fahrenheit, and they'll turn on all the air conditioners, they'll turn on all the ceiling fans, even though they don't realize that if no one's actually in the building, a ceiling fan isn't going to help at all. A ceiling fan doesn't cool air. It will cool you if you're standing below it, but it won't cool the air. So I think basic knowledge like that is being kind of forgotten, and people's behavior is an outcome of that knowledge being lost. In a way, they're things that are kind of mundane. They're not as sort of splashy and flashy as, say, wind towers from Iran or muscates from Oman that use principles similar to the project that I did. But what's something that's very important to remember, so the house where I am right now, it was built in 1919, and it has like walls that are a foot thick. This is the way you build in Germany and a lot of continental Europe. And early in the morning, you can flush the house with cool air and then close the doors, put down awnings or rolladen, and keep the sun load out of the house. And without air conditioning, you can, unless it's like 100 degrees Fahrenheit out, you can keep an indoor space relatively comfortable just by using just common sense and long-held techniques that in America have completely disappeared. Things like shutters are just these, very decorative accessories. But shutters also in this house are used very functionally and very effectively.
In the end, Brooke says that we all maybe need to shift our mindset to consider what we really want out of new technology. When we say solutions like shutters and thicker walls are mundane, we're looking for a solution that feels more exciting. But maybe we need to realize that technology doesn't need to be fancy or splashy or exciting to have an exciting impact. Take those thicker walls. Even improving the insulation inside them is a simple, yes, maybe even mundane way to make our spaces more comfortable, but it can make a huge difference on the livability of a home. Clay, as it turns out, has a role to play there as well.
Clay is known for thousands of years as a material that has a distinct property profile. But to make something new out of it, we also have nowadays with chemistry a new toolbox to bring it also in different aspects with different functions into a new environment in the end. So, and this is why we take the clay that is known and combine it with a lot of new technologies that we elaborated in BASF, for example. And then we can create something completely new for a completely new application.
Substance.
My name is Frank Reuter. I'm chemist by training, 15 years working for BASF, and my current title is the Business Manager Cavipor, which sounds a bit boring because it describes just a small portion of my everyday work.
The fact is, putting thick walls on a house doesn't do much if the stuff those walls are made of just lets heat pass through easily. So insulation is key, and innovations in this area can have a huge impact. Most insulation on the market today comes from fossil fuels. In contrast, Cavipor is made from the same minerals found in clay. But those minerals don't need to be sculpted or fired like most other clays. Instead, they're part of a foam that flows into the smallest cracks behind walls and then solidifies as it dries, making an effective insulator.
It's not just clay, it's not just foam, but it's more or less an orchestra of different ingredients. So we have not just clay as a mineral, but we also have 4 other mineral materials that's inside. We have the polymer, that's the glue in the end. We also have a material inside that leads to water repelling effect. This is really something that we also invented. And you find also the clay foam homepage, for example, as a central point of information for our customers, but also for house owners, where they can get a lot of information independent from the brand Cavipor. And something like that is really unique and new to the market. So there are some mineral-based foams out there, which are mostly cement-based. But this is totally different in Cavipor because the process of hardening, of gluing together, this is nothing compared to cementous, but it's more like polymer chemistry that we use.
Cavipor combines a soap-like foam that acts as a scaffolding for tiny mineral particles and a small amount of a polymer that helps those mineral particles stay in place. The third ingredient, which is called a crosslinker, turns this freshly created flowable foam into a more solid material and just takes about 2 minutes. It's like firing the clay, but without all the heat.
When it sets, then it has the consistency of mousse au chocolat. So that's the consistency that describes best for the wet, so the fresh foam. You have very lightweight, grayish, porous material.
As the foam dries, it becomes spongy and pores open up. The final material takes a few months to dry. After that, it's 90% mineral-based. And even though the whole system starts out dissolved in water, after it dries, water actually can't pass through, at least not when it's a liquid. Air and moisture can still pass through because the microscopic pores allow the walls to breathe, so that Cavipor insulates from heat in the summer and cold in the winter without completely sealing up your house. And it can also notably dampen ambient noise. This is sounding pretty nice for a studio.
That's the magic of chemistry. So we have a little additive inside that is water soluble. But after the drying process, it is water repelling. So it's really a total phase change of this material in the combination of all the other ingredients that are in the clay foam system. And yeah, that leads to the effect that you really see the water droplets, they stay on the surface of this porous material. So it really looks pretty insane, but that's very fascinating, yeah.
Because it's made mostly of minerals, Cavipor isn't just liquid water repellent, it's also flame retardant. And because the minerals and other materials inside it are harmless, it can be recycled or disposed of right alongside other building materials. This gives homeowners a more comfortable and energy-efficient house without the trade-offs that are usually required to update it.
The unique property of Cavipor is the combination of all the properties that it brings with. So it's the recyclability, it's the water repellence, it's the non-flammability, and of course, it's the ease of application. So people that work with the material, so they don't want to have some itchiness or scratchiness after a day of application. There should be no bad smell, and of course, no hazardous material inside that they breathe in every day.
Frank says that any wall with an open cavity can be filled with Cavipor by technicians who are trained to work with it, without all that mess required to insulate walls using conventional insulation materials. No dust and no need to tear open your walls.
If you think of an existing house, a family living in the house, you will not tear down the wall, fill the cavity, and then build up the wall again. So we drill a hole, we put the nozzle into this hole, and then we let the flowable foam be injected into this cavity. Together with the technology partner from ours, we developed a machine, an automated machine that works just dedicated for Cavipor. And now we're in the 4th generation. Working on the construction side, it's more or less just pressing one button, 2 buttons. The machine is automated and knowing how the 3 components and the air are brought together. So step 1, it's the foam creation from the soap. Step 2, admixture of the filler. And step 3, admixture of the crosslinker. And then the flowable foam is injected through the nozzle into the cavity. And what the contractor, the installer, should know is how to push the button in the right way and how to clean the machine in the end. But that's it. After the first, I would say 2 to 3 houses, the installers are more expert than we are in the application aspect.
Frank has been working with the Cavipor team since its earliest research phase in 2012 and took over the project in 2015. After screening more than 6,000 different formulations, the composition was certified in Germany and started appearing in the first homes in 2019. Today, it's earned European certification, and thousands of homes across Europe and the UK are insulated with this clay foam system.
I love this work. And I love the way we work together, so not just me, but the team, and fulfilling all the tasks that it needs to develop a new material, to bring it into market, to format the product, to convince customers to be successful in this business management that we do, but also in move on in developing this material and combining all the disciplines. Our little team, we're 4 people in the lab and 3 people in the management. And with that, I would say that we're some kind of BASF internal startup because we have our own little world in which we can work and can move and be successful. Of course, we all want to have a nice future on a nice planet, and we have just limited resources of fuels and energy, and this is why we wisely should use the energy. It's also in the interest of a company like BASF to be, on the one hand side, pretty profitable, to be really just at the trend of the time or perhaps even a bit ahead. So to offering in its portfolio really the innovations that are needed today or perhaps also tomorrow.
The move to a more sustainable future requires more than just innovation. It requires us to shift our mindset. but not just toward prioritizing energy efficiency and a healthy environment, which, to be clear, we definitely need to do. We also need to recognize that simple-sounding solutions can also be groundbreaking, that invention needs a purpose beyond just novelty, and that technologies from the past aren't just old-fashioned, but they can be founts of knowledge that can be tapped and drawn from like any other resource.
I could see just sort of more modern expressions of these older technologies. So it's not about regurgitating them or making them, it's not about the history book and making them going back in time for nostalgic reasons. It's about learning what's valuable about these technologies and bringing them into the present for today's context.
We'll be off in the month of August, trying to stay cool, but we'll be back in September where we'll be talking about enzymes. Join us on our next episode to look at that and more. This has been Substance, stories about the stuff that shapes our world. Substance is a podcast by BASF, produced by Territory Agency in collaboration with WakeWord and me, Joe Hanson. Research and scripting by Danielle Sedbrook, Claudia Doyle, Hardy Reuter, and Joe Hanson.